with number 31. This is from the tutorial book. The question gives you two numbers, which I will denote z and w. And the question goes, it says find the product z times w in two ways. And when they say in two ways, they mean in Cartesian form and in polar form. In Cartesian form, this is very straightforward. We just have to put these two numbers next to each other and do the complete expansion. And I will do it, but I will do it a bit later. First, I will focus on polar form, on the second way of finding this product. And when I do that, the first step towards the answer, towards finding this product in polar form will be converting these two numbers into polar form or into exponential form individually. This is something we discussed with you last week. I told you last week that if you have a complex number given in algebraic form like so, a plus ib, you can always convert this into the trigonometric or exponential form. Remember, I don't make any difference between these two terms. Exponential form and trigonometric form, it's this identical thing to me. You can convert it into the form like this by taking r, which is the modulus, by computing r like this. It's a very easy part. The harder part is identification of this theta angle of the argument of your complex number. And I told you the general look of the formula is like this: r cos of the fraction like so, in case UB is non-negative, or you have to go negative, such r cos, in case your B is negative. I said non-negative here, hopefully. I mean non-negative here. It's not an easy formula to apply, but luckily, most of the time you won't need this formula. 8 out of 10 times you will be able to guess the argument just by looking at the complex number. And in this particular question, that will be the case. By looking at these numbers, we will be able to guess those arguments. Look at this. For instance, for the first number, z, this number. First, I identify the absolute value of this number, the modulus. This is easy. I have to take the sum of the squares of the real and imaginary part. So it's a 1 plus 3, 4. Root gives you 2. So here it is. Now I intentionally factor it out. I write my z number like this. I factor out the modulus. And then by looking at these two numbers, I'm trying to guess the theta angle, which will make this number cos of that angle and this number sine of that angle. If you know the standard values of cos and sine, such a guessing will be quite successful most of the time. So in this case, my guessing gives me that the cos will be of pi and 3 and the sine will be of pi and 3. So the angle we can choose is pi and 3. Or you can write this in exponential form like this. Like this. Similar argument for the w. Again, first I identify the absolute, the modulus of this complex number. Here's the formula for the modulus. So in this case, it's 1 plus 1 and then square root, which makes it root 2. Now I factor it out. Here's my square root. Here's the result of the factorization. And then again, the guessing machine starts. I'm trying to guess an angle such that cos of this angle is this number, and sine of this angle is this number. Again, it's a very easy guess. It's a pi and 4. And here's my trigonometric form, or exponential form if you wish. On both occasions, pay attention, we found an angle theta, which is within the range negative pi, pi. So in fact, we found the principal argument, and we found it without using this formula. That's interesting. There will be a few examples where you will need such a formula, such an insight. I don't think I will present this in class, but in your tutorial classes, you will have such an examples. If you read through the questions, you should raise this with your tutor, I mean, if you want to see the solution to that question, unless you can find it yourself. I have a picture here. Let me just picture these numbers for you. Here's my complex numbers, blue vectors that represent these two numbers. The lower one, it's the W complex number, 1 plus 1, so this is the real part. 1. This is the real part, imaginary part of this number is I. The other vector is, Z. It has identical real part, it's also 1. You see 1 here and 1 here. For the imaginary part, you have I root 3. And we now know the angles, or we know the lengths of these vectors, right? This is a root 2 length, here it is. This is the exactly 2, here it is, the absolute value of the modulus. We also know the angles. This angle is pi and 4. And this angle is pi on 3. So the first stage of my solution, we now finished it. We found the trigonometric forms for these two complex numbers. Now we can address this question. We can find the product, ZW, in two ways. Like I said, one way is a Cartesian way. We will do it. It's very straightforward. I have it on my slide a bit further to the end. The first way is the trigonometric way, and now we can just simply use the fact that if you multiply two complex numbers given in trigonometric form, it's simply just multiplying the moduli and adding up the arguments. So here it is. Or actually, as a matter of fact, my first line here on my slide, it's the Cartesian way of finding the product. So that's what I promised here. You put these two numbers next to each other and you just do a simple expansion. I'm not going to do it on the slide, it takes too much space. It's a very elementary arithmetic. I hide this with the dots, but the result of that, here it is. You can easily actually check these numbers because the real part of the expansion will be when you multiply this one with this one and this I root 3 with this I, which makes it negative root 3. Here it is. And the imaginary part will come up if you multiply this I with 1 and this I with this 1. Here it is. Now in trigonometric form, here's my product again. Here I multiply the moduli, one moduli with the other moduli, one modulus with the other modulus, and then I add up the arguments. And I use the exp notation now because it takes less space, obviously. I use this exponent form of my trigonometric or exponential form. So when you add up these arguments, here's your exponential form. And technically the question is over now. We found the product ZW in two ways. Yeah, technically the question is over now. However, we can take this question one step further because by having this ZW product in two different ways, we can actually extract more information from this. For instance, this number, if you take this exponent, if you expand this exponential form into the trigonometric way, so if you write cos of 7 pi on 12 plus I sine of 7 pi on 12, right? If you do that, then obviously you can identify the real part with this real part and the imaginary part with this imaginary part, which means now you have a very easy way of finding the exact value for sine and cos of this special angle, 7 pi and 12. Actually, it goes towards the collection of the special angles we know sine and cos for. For instance, if you remember last time at the end of the lecture, we computed with you the sharp exact value for sine of pi and 5. And by implication, you can also do it for the cos of pi and 5, and 2 pi and 5 as well. Well, this example gives me the opportunity to find the cos and sine of 7 pi and 12. Here it is. Cos 7 pi and 12, that is the real part of this number, and that is another alternative expression for the real part of the same number. So the cos will be the real part of the ZW product by the absolute value of the ZW product. Now we know everything here, and that's the value for the cos 7 pi and 12. Similar argument will work for the sine. Sine of 7 pi and 12 will be the quotient of imaginary part of the ZW product by the absolute value of the ZW product. All of these values are known to us now. Here's the imaginary part. Here's the absolute value. And that's the final value for the sine of 7 pi and 12. Geometrically, I think I have it on my picture here. The product vector is the red vector, which represents exactly the product, ZW. Is the product ZW. For this ZW, we know now everything. We know the imaginary part, sorry, the real part. Here it is. We know the imaginary part. Here it is. We know the angle, 7 pi and 12, and we know everything basically.